This is 3.5 Kinetic Molecular Theory. Our outcome is I can explain the relationship between the motion of particles and their macroscopic properties. So we're trying to connect how the motion of particles in a gas relates to its macroscopic properties like pressure, temperature, and volume. So we're going to do that using kinetic molecular theory, KMT, as well as particulate models and graphs. So the kinetic molecular theory is a model to help us explain behavior. So models are successful if it explains what we observe and it can predict the results of future experiments. So no model can ever be proven as correct. They're all just based on experimental results. So we use simple models to predict approximate behavior, where we'll need to use more complex models to account for very precisely observed quantitative behavior. So the KMT is a simple model used to explain the properties of gases. So we have to assume that the gases follow these behaviors here, these postulates. So gas particles are small compared to the distances between them, so we might as well say that they have no volume. The particles are assumed to exert no forces, no attraction or repulsion. The particles are in constant random motion, and collisions exert gas pressure, and those collisions are elastic, meaning no energy is lost. So energy might be transferred from one particle to another, but the total energy is constant. And the average kinetic energy of a collection of gas particles is directly proportional to their Kelvin temperature. That's why we always use Kelvin with these gas law problems. So each of the following are behaviors of gases that contradict these postulates that we just went over. So we know that water vapor condenses into liquid water. So postulate B, which says there's no intermolecular attractions, can't really be true. Particles take up space and they can be compressed greatly but not completely. And this is going to contradict postulate A, which assumes that the volume of the particles is so small compared to the volume of the gas that it might as well be zero. And kinetic energy may be lost as heat after particles collide. This contradicts postulate C. So why do we use this kinetic molecular theory when we see so many behaviors that contradict its postulates? And that's because it's a simple model that does well in predicting gas behaviors under most conditions. So under most conditions, this is good enough for us to understand the behavior of gas particles. And what's important is that it's a simple model. So this helps us really understand kind of approximate behavior of gases. So let's talk about temperature. So the Kelvin temperature of a collection of gas particles is proportionate to its kinetic energy. So here we have an equation here. Ke average is 3/2 RT. So looking at these 4 samples of gases, how does the average kinetic energy of 2 particles at the same temperature compare? So if those particles are at the same temperature, they have the same average kinetic energy. What is the relationship between average kinetic energy and temperature? So as you increase the temperature, those particles are going to absorb that energy and it's going to increase their motion. It's going to increase their kinetic energy. So looking at kinetic energy and how that relates to velocity, how that relates to speed here. So if we look at individual gas particles, they're going to have different speeds even if they're at the same temperature. And that's because each molecule has slightly different kinetic energy. So they all have the same average kinetic energy, but if you look at each individual particle, we see that there's a range of kinetic energies. So a way that we can calculate that is 1/2 mv squared. In chemistry, we use what's called the root mean square speed, but it's still just a velocity. So looking at these flasks, which gas will have the particles with the highest average kinetic energy? They're all the same temperature, so they have the same average kinetic energy. But that doesn't mean that every particle has the same kinetic energy. There'll be some with a little bit of kinetic energy and some with a lot, but that will all average together. So, in which gas will the molecules have the greatest average velocity? So, it's going to be hydrogen. If we look at our equation, Ke equals 1/2 mv squared. So, all of these have the same average kinetic energy. So, for that to be true, if we have a lighter particle, if the mass is lower, it has to travel at a higher speed to keep the same average kinetic energy. So this leads us to the Maxwell-Boltzmann distribution. So this shows us the distribution of kinetic energies of particles at a given temperature, which is another way of saying it shows their velocities. So here we have 3 gases, and we want to compare the velocity of the particles for each temperature. So the average velocity is going to occur right underneath the curve of the bell curve here. So right underneath that peak is where we're going to find that speed, that velocity. So for 273 Kelvin, it's about 400 meters per second. At 1,000 degrees higher, it's about 1,000 meters per second. And another 1,000 degrees higher than that, and we're at about 1,400 meters per second. So what happens to the peak and the range of velocities as the temperature of the gas is increased? So at higher temperatures, there's this wider distribution of velocities. So underneath that peak, that gives us the most probable velocity. But it's important to know that when we observe gases, we are seeing an average behavior of those molecular interactions. So the range for 273 goes from 0 to about 1400. For 1273, it goes from 0 to 2500. It's got a wider range. And then for the hottest gas here, we have even a bigger range. So for a cooler gas, most particles are going to be right around the average. But as you increase the temperature, you're going to get more particles at the extreme ends of our distribution. So what is the relationship between temperature, kinetic energy, and velocity? So as temperature increases, the gas particles gain kinetic energy and their velocity is going to increase. An application of this different behavior is effusion and diffusion. So diffusion describes the mixing of gases, whereas effusion is a very specific phenomena. So it's how quickly a gas travels through a pinhole into a vacuum chamber. So the rate of that effusion depends directly on the velocity and thus the temperature. But then it also means that it relates to the mass of the particles as well. So Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of the mass of its particles. So just to point out, this is the square root of m2, and here we have gas 1 on top. Here I have gas 2 on bottom, and m1 is on bottom here. So the effusion rate for an unknown gas is found to be 31.5 milliliters per minute. Under identical conditions, the effusion rate for oxygen is 30.50 milliliters per minute. So which of these gases could it be? So the unknown gas effuses faster than oxygen gas. So this means that the unknown gas must be something with a lighter molar mass than carbon dioxide. So if I do my math here, I'm solving for the mass of my unknown gas here. So 31.50 is on bottom here and X is on top here. So with a little bit of arrangement and manipulation, do the division, do the square to cancel out the square root. we get that X is 30 grams per mole, which is the molar mass of nitrogen monoxide. We can also apply this phenomena into how to separate particles by different masses. So, for example, if we look at carbon monoxide, so these particles are going to effuse based on their mass. So the lightest molar mass is going to effuse the fastest because it has the highest velocity. And the highest molar mass will diffuse the slowest. So for number 1 here in our reflection questions, we want to compare the 3 gases in the Maxwell-Boltzmann distribution. So you would need to show that as the temperature increases, we get a wider range of those velocities in the gas.